Hey everyone, welcome. Today, we're going to crack the code on a really powerful and sometimes kind of tricky programming concept called recursion. And we're going to do it by tackling a super simple, fun puzzle that's going to make this whole idea click. All right, so here's the game plan for today. First up, we'll lay out the puzzle we're trying to solve. Then we'll get into the mindset of thinking recursively. After that, we'll translate that idea into code, and then we'll take a peek under the hood to see how the computer's memory, the call stack, handles it all. And finally, we'll wrap up by seeing why this approach is just a perfect match for our puzzle. Okay, first things first. Let's make sure we're all on the same page. The actual problem we're solving today is really straightforward. You've probably seen it a million times before.
Yeah, just like you see here. A palindrome is simply a word that reads the same forwards as it does backward. You know, race car is the classic example. Reads the same no matter which way you look at it. Hello, on the other hand, well, not so much.
But here's the twist. The real challenge for us today isn't just spotting a palindrome. The goal is to solve this using a very specific, and I think very elegant, technique called recursion. And this is the important part, we have to do it without using any standard loops. That's the key rule here.
All right, now for the main event. How do we start thinking recursively? It's a whole different way of looking at problems. The subtitle here says it all, peeling the onion. We're not going to try to solve the whole thing at once. We're going to peel it back layer by layer until we get to a core that's so simple it's trivial to solve.
And this, right here, this is the golden rule. This is the heart and soul of our recursive logic. We just ask two simple questions. 1, do the first and last letters match? And 2, is the stuff left in the middle also a palindrome? And that second question, that's the secret sauce. That's where the magic of the function calling itself happens. So let's walk through it with Madam. You can literally see the problem shrink. Step 1, we look at Madam. Are the ends the same? Yep, M and M. Great. Now forget the M's. Our new, smaller problem is just oughta. So we ask again, do the ends of oughta match? Yep, A and A. Cool. Our next problem is just D, and a single letter is always a palindrome, right? So boom, we've hit what's called our base case. The problem can't get any simpler. Okay, so the idea of shrinking the problem makes sense. But how in the world do we translate that into actual code? You know, into instructions a computer can actually understand and follow. Let's look at the blueprint.
So, any good recursive function needs an escape plan. It has to know when to stop calling itself. We call these base cases. We actually have two. Plan A, if the string is super tiny, one letter, or even empty, it's a palindrome. Done. Return true. Plan B, if those outer letters don't match at any point, game over, it's not a palindrome. Return false immediately. And if neither of those things are true, well, that's our recursive step. We just run the whole check again on that smaller middle piece.
All right, now this is where things get really cool. We're going to pull back the curtain and look at how the computer's brain, its short-term memory, actually handles all of this without getting confused. This is the call stack. You know, this is probably the biggest question people have when they first learn recursion. If a function just keeps calling itself over and over, how does it not get lost in a total mess? How does it keep track of everything? Well, the answer is a beautifully simple structure.
Okay, let's trace it. The very first time we call our function, we give it the whole word, Madam. It checks the first and last letters, M and M. Hey, a match. Awesome. But it can't finish yet. It needs to know if the middle part, Ada, is also a palindrome. So it literally pauses its own work and makes a new call to itself.
And the way the computer keeps track of this is with something called the call stack. The easiest way to picture it? Just think of a stack of plates. Our first job, checking Madam, is the bottom plate. The new, smaller job, checking Ada, gets put right on top of it. Now, here's the key. The computer only ever works on the very top plate of the stack. So it looks at that top job, checking Adada. The ends match, ah and ah. Great. So what does it do? You guessed it. It pauses that job and puts an even smaller job on top of the stack, checking the single letter D. And look at our stack now. We've got 3 jobs piled up. Each one is just sitting there, patiently waiting for the one on top of it to finish its work and report back. Okay, now we're at the top of the stack. This job is super easy. Check deed. Since the start and end are the same letter, we've hit our base case. It knows the answer instantly. True. No more calls needed. And this. This is the crucial turning point. The chain reaction is about to happen in reverse.
So that top job is done. It shouts true, down to the job waiting below it, and then poof, it's popped off the stack. It's gone.
Now, that middle job can finally wake up. It says, okay, my letters A and A matched, and the job I was waiting on just told me true. So its job is also complete. It passes its own true result down to the bottom plate, and then poof, it's gone too.
And at last, we're back to our original job, the one that started it all. It gets the true it's been waiting for this whole time. It already knows its own M's matched, so now it has the final answer. The whole word is a palindrome, it returns true, and the stack is now empty. We did it.
Okay, after seeing all that stacking and unstacking, you might be thinking, whoa, why go through all that trouble? Why is this recursive way of doing things considered so elegant for this specific problem?
When you really break it down, the whole thing is just a super simple, repeatable pattern. Check the ends, then shrink the problem. And as we just saw, that stacking and unstacking process, that's exactly what the call stack was designed to do perfectly.
And that's the real takeaway here. It's all about matching the solution to the problem. The problem of a palindrome has a naturally recursive structure, right? It's just mirrored ends around a smaller version of the same problem. Our code just mirrors that exact same beautiful, simple structure.
And you know, this way of thinking, breaking a big problem into smaller, self-similar pieces, it's not just for code puzzles. It's everywhere. It's used for sorting files, for drawing complex patterns in nature, even for things like family trees. So the real question to leave you with is, now that you know how to spot this pattern, what other big problems can you solve by just breaking them down?